Now, you know that we can present the numbers in the BCD code form. And also we have learned in the previous chapters that we can add two numbers which are represented in the form of the BCD. Now we want to design a circuit to add two numbers which are written in the form of the BCD. First of all, we have to uh, derive the truth table for the BCD adder. How we can do it? If you remember, we said that suppose that we have one number, the second number, one bit, actually one number between 0 up to 9. Now we can represent this one number in the 4 bits. And also because the BCD code, the maximum value of the BCD code is 9, when we add these two 9 with together, we will have 18. And also we can have one another carry. This carry also will be added to the 18, which is equal to 19. So it means that in the decimal form, we can actually investigate the numbers between 0 up to 19 to see that what's happening when we have two BCD numbers when we want to add these two with together. Now, for representing the 0 up to 19, we need to have the 5 bits. So we called these bits in this form: Z1, Z2, Z4, Z8, and K. Now, we say that if the addition of two BCD code is between 0 up to 9, we write the corresponding binary of the 0 up to 9. And also, if the addition of two BCD codes are between 10 up to 19, also we can write the corresponding binary numbers of each numbers. Now, what's happening when the addition of two BCD code is between 0 and 9? We said that when the BCD addition is between 0 and 9, same thing is written in the output. So in the output also we will have S1, S2, S4, S8 and also carry. We say that the numbers between 0 and 9 directly written in the output, because we don't need to add anything to the output, because the addition is in the range of the BCD code. But when our addition is more than 9, it means that is between 10 up to 19, we have to add 6 to these numbers to find the result. We apply everything like the theory that we have learned in the BCD addition in the truth table. Again, look at to this section. Here, the addition between 0 up to 9 directly is written in the output. But if addition of two BCD numbers is more than 9, between 10 up to 19, added by 6, then written in the output. Now we have to find the output of the Boolean function of each output. How many output do I have? 1, 2, 3, 4, 5. But you can see that I cannot use the Carnot map because we have 5 inputs. So using the heuristic method, we have to find this concept. Now look at here. How can I find that? You can see that if you look at to this truth table, you can see that when I have to add 6 to the numbers, the value of the C is 1. Okay, so it means that with checking the C, we can understand that we have to add 6. But how? Look at here. If you look at the numbers between 16 up to 19, you can see that the value of k is equal to 1. It means that when after adding two BCD codes with together, when the last bit is 1, it means that always we have to add 6. I could find the one of the conditions that I have to add 6 to it. Now look at to the rest of the numbers. In the numbers between 12 up to 15, you can see that Z8 and Z4, when Z8 and Z4, both of them simultaneously are equal to 1, again we have to add 6 to the result to get the correct result. What about the 10 and 11? If you check these two, you can see that when Z8 and Z2 simultaneously are equal to 1, so we can see that we have to add 6. For the rest of the numbers, all of them directly is written in the output. So I could find the conditions that when one of them happens, we have to add 6. Now how we can draw the actually digital design of these conditions? We say that when Z8 and Z2 both of them are 1, when Z8 and Z4 both of them are 1, or k is equal to 1, we have to add 6. So it means that for this concept, I can use the AND gate for Z8, Z2, AND gate for Z8, Z4, and because I said that one of them happens we have to 6, means that using the OR gate, we can produce the C. After producing the C, we will not have any problem because we said that you can see that here using this circuit that you can see here, when C is equal to 1, means that we have to add 6. When C is equal to 0, we don't need to add 6 and directly the input goes to the output. Now, how we find Z1, Z2, Z4, Z8 and K using with adding the two numbers with together. So it means that at the end, after finding the Boolean function of the C, we can have this circuit. Now look at here. Here, two numbers, which is written as a 4-bit in the BCD code. For example, suppose that here is, I don't know, 8, here is 2. The BCD code of 8 in the 4-bit is written here. The BCD code of 2 in the 4-bit is written here. Using the 4-bit binary adder, 4 full adder here, the Z1, Z2, Z4, Z8, and also K calculated. Now, this is the circuit of the previous slide connected here. The C produced comes here. You can see that this is 0 and this comes from this line comes from the C. Now look at here. When C is equal to 0, these 2 bits is equal to 0 and these 2 bit also is equal to 0. Okay, so what does it mean? It means that this Z1, Z2, Z4, Z8 that directly comes here added by 0. It means that directly in the result, again, we can have the Z1, Z2, Z4, Z8 as S1 up to S8. And again, we have to use the another binary adder here. But if the C is equal to 1, it means that this 2 is equal to 1. So when these two bits is equal to 1, what we'll have here? 0, 1, 1, 0. It means that the result of addition will be added by 6 to get the output of the system. Now, using an example, if I want to explain this one, I will have something like that. Now look at here. Suppose that I have 2, which is written in the decimal, and I don't know 5 written in the decimal. I want to write the BCD of this one. The BCD of this one is equal to 0, 0, 1, 0. And the 5 is the 0, 1, 0, 1. So it means that here is 0, 1, 0, 1. And here is 0, 0, 1, 0. Okay, now using this full adder inside of this box, the Z1, Z2, Z4, Z8 are produced, and also K are produced. Now, because we know that the addition of these two, now if I write in this form, 0, 1, 0, 0, the addition of these two will be less than 9, This K, and also actually this C will be equal to 0. Because you can see that here, this is the K, this is the Z8, this is the, and actually the rest of them. So, because the C is equal to 0, here is equal to 0, 0, 0, 0. And also 1, 1, 1, 0 comes here. Now 1, 0, 1, 1, 1 plus 0, 0, 0 is equal to 1, 1, 1, 0. So I could find the result. Similarly, for the another example, if we suppose that we have something like that, for example, I don't know, 7 and 5. Okay, so the BCD of these 7 is 0, 1, 1, 1 and 0, 1, 0, 1. If we add these two together, again 1, 1, 1, 0, 1, 0, 1, 0 is written here. Again here calculated. So we will have something like that. 0, 0, 1, 1. So here we will have 0, 0, 1, 1. Okay. Now, in this case, because this value is greater than the 9, this C will be equal to 1. Now, what do? We add this 1 with the 6. Now, here will be equal to 1, 1. Here will be equal to 0, 0. And 0, 0, 1, 1 comes from here. Now we have to add these two together. So at the end, we will have the result. This is the concept of the BCD adder that you can see here. Now, in the case of the binary multiplier, suppose that we have 2-bit by 2-bit binary numbers. We want to multiply them, and actually we want to implement the digital circuit. So you know that from the primary school, we know that if we have two numbers with together, we can multiply the numbers in this form: a0 multiplied by b0, and a0 b1, again a1 b0, a1 b1, then add all of them with together. Now you can see that for the b0 and is a0, we have AND gate, and we have AND here, and here, and here. Then we have the addition of the 2 bits. So as a result, we can draw this circuit to producing the multiplication of these two numbers with together. From here, a0 and b0 directly comes to produce the p0, like this one. And also a0 b1 added by the a1 b0 using the half adder. Why? Because we have 2 bit here, 1 bit, second bit. Using 1/2 adder, we can produce the p1. And for the adding these 2 bit, maybe we can have carry. This carry from here comes here, we know that. It means that here from here, the carry from here comes here. And again, the carry of the previous one is added by a1 b1, which comes from here, to produce the p3 and p2. Using this concept, you can extend this multiplication by 3-bit by 4-bit binary multipliers and produce the binary multipliers and also the other multiplication. So if you look at to this example, if we have 4-bit by 3-bit binary multiplier, according to same concept, if you write the theory of the multiplication of these two binary numbers with together, you can see that we need to have 2 4-bit adder for producing the actually multiplication of these binary numbers.